Today we will discuss how binary division is carried out and how we build a circuit to carry that out for a processor. We have been discussing various arithmetic operations and logical operations, and we have discussed design of ALU. Last we discussed was how we carry out multiplication, and we talked about different designs of multipliers. We will continue with that, talk of binary division and design of divider. First of all, I will summarize how we did multiplication, because there is some overall similarity between how multiplication and division is carried out, and we will illustrate division operation by an example by taking two numbers the same way we did for multiplication. Then from that we will derive the algorithms. We will ensure that algorithms we are talking of are correct and discuss the circuits. Initially we will talk of unsigned division and then talk about signed division. So, just to summarize what we did for multiplication, we looked at an example and saw that when you work on paper, how you manually carry out multiplication. So, the same process was captured by a circuit. We went through a set of refinements, and finally, we had a circuit and algorithm which looked like this. Okay, essentially, the multiplication operation was broken down into shifting and adding. So, we then saw that for signed multiplication, you need the ability to add and subtract, and we talked about Booth's algorithm. So, we also discussed the range of values which could result when you multiply, and there are two types of multiplication in MIPS, which try to produce signed result or unsigned result, and there are also pseudo instructions which work with a single word output. Normally, when you are multiplying two one word integers, the output could be accommodated in two words. So, there are pseudo instructions which will check if the output is exceeding one word and accordingly give overflow. Okay, so, now let us start with division by taking two small 4-bit numbers and trying to see how division is carried out. So, let us say we have a number 00001101, which stands for 13, how that is carried out, how that is divided by a number 0100, which is 4 in terms of its binary equivalent. So, we will expect that when you divide 13 by 4, you get 3 as the quotient. So, in anticipation I have put that here, and we should be left with 1 as a remainder. So, naturally this division would be carried out as a set of shift and subtract operations. So, initially we see if this divider can be placed in this position here, and we can subtract. So, we examine this position, because this will correspond to a bit in the LSB position for the quotient. Okay. So, we are now targeting for a 4-bit quotient. We have a 4-bit divider, and if we are able to subtract 0100 in this position, then it will result in a 1 here, but in this case we cannot, because this is larger in this position. We are only subtracting a 0, okay, and we place a 0 bit as part of the result. So, after subtraction we still have the same number, and next time we try subtracting in this position. So, that leads to another 0 bit for the result, and there is no change here. Okay. So, we get 0011. I am just dropping off zeros from the left side, which are insignificant. Then we try subtracting in this position. okay, and indeed now we can subtract. So, we get a 1 in the quotient, and after subtraction we get 0 0 1 0 1. Then finally, we subtract in this position, which is right justified, okay, and this results in a 1 in the LSB of the quotient, and finally, there is a remainder 1. Okay. So, we carried out these 4 steps. At each step we tried to see if we can subtract or not. If subtraction was possible, subtraction was carried out, and 1 gets recorded in the result. If subtraction is not carried out, a 0 gets recorded in the result. So, that is a very simple mapping of normal decimal division we are used to in binary domain. Okay. So, we require basically comparison. Before we can subtract, we compare, if necessary we subtract, and we record a 0 or 1, and from step to step we shift the position of the divider. So, that in nutshell is the result. You would notice, let us call this as A, which is the dividend, divisor is B, quotient is Q, remainder is R, and the values which are being subtracted are nothing but multiples of B, the divisor, multiplied with powers of 2, okay, and weighted with either a 0 or a 1. So, in the first position it was B multiplied with 2 raised power 3, which we tried to subtract from here. So, you could see that B has been shifted 3 bits to the left in relation to A, and in position number 3, okay, counting it as 0 1 2 3 in Q, we record the result as a bit 0. So, next time the attempt was to subtract B into 2 raised power 2, and then B into 2 raised power 1 and B into 2 raised power 0. The last value being subtracted is actually 0 1 0 0 and not 0 1 0 1. What we are trying to get is given A and B, we are trying to find Q and R which will satisfy this. So, we take a register R which we initialize with A. A is the dividend, and from this we will keep subtracting. Hopefully, what will be left in A, left in R would be the remainder. Okay. The quotient Q initially is put as all zeros, and another register D which will hold the value B, which is the divider. Okay. So, then there is a loop where we repeat this comparison and subtraction step. So, if D multiplied by appropriate power of 2 is less than R. Okay. So, this is D positioned at appropriate position. So, you would notice that when I equal to 0, in the beginning, in the first step, you need to displace it by n minus 1 positions. Okay. So, with I equal to 0, the power of 2 is 2 raised power n minus 1. So, that is in our case n was 4. Okay. So, we had shifted the divider by 3 position to the left. So, we are comparing it with R, and if this holds, then R is replaced with R minus D into same factor, and Q n minus 1, that particular bit of Q is recorded as 1. Okay. If the condition does not hold, we do not really have to carry out, either you say subtract 0 or you just leave R as it is, and the corresponding bit of the quotient is recorded as 0. Okay. Simply then step up I and repeat it for n steps. Okay. Is it clear? So, this is our basic unsigned division algorithm. We will analyze it to make sure that what we are doing is correct, and then we will do some modifications, some improvements, transformations, and implement this in form of a circuit. Okay. So, we want to make sure that what we are doing actually computes what we want. Okay. So, our requirement is that ultimately there is a loop which is executed, and we will ensure that there is certain invariant it maintains. Okay. We will ensure that q into d plus r is always equal to a. So, as the loop proceeds, this will be ensured, and also we will ensure that r remains within this limit. Okay. So intuitively we have put up this invariant, and first of all we must make sure that this invariant is a useful one, which will give us the required result. So, at the end of the program, when the loop ends, I would have reached a value of n, and if we put n in this invariant, put I equal to n in this variant, this will ensure that the remainder we are getting is less than the divider. You see this equality a equal to q d plus r can be satisfied by many q r combinations, right. We are given a and d, d is initially b, okay, and we are finding q and r, quotient and the remainder. So, this is a single equation with two given values, and there are multiple q r combination which can satisfy. We want the one where r is within 0 and d. Okay. The remainder should be less than the divider, and it should be positive, non negative I should say. So, with I equal to n, this condition will be ensured. So, at the end of the program, if we are ensuring this loop invariant, then we have the right quotient and remainder, and remainder is within the range we expect it to be. Okay. So, therefore, r is the correct remainder and q is the correct quotient. So, this is to show that the loop invariant we are talking of is a meaningful one. It will actually ensure that we are getting a correct result. Now, let us prove it inductively. Okay. First, we will ensure that this holds in the beginning. Okay. When I equal to 0, when you start after initialization, this holds or not. So, our step 1, which is initialization, is making I equal to 0, r equal to a, q equal to 0 and d equal to b. So, if you put these values, then we can initially be sure that this holds, right, because q is 0 and r equal to a, right, which is ensured by this initialization. Okay. So, this holds. In this, if you put r equal to a and q equal to 0, it is satisfied. And also, since I is 0, this relationship that a is less than if a is less than b into 2 raised to the power n, then this will also hold. Okay. Now, how do we meet this condition? See, initially r is same as a and d is same as b. So, and I is 0. So, in order to ensure this, what we need is a should be less than b into 2 raised to the power n. Okay. So, if we assume that a is n bit number, okay, and b is not 0, so b is at least 1, then a is less than 2 raised to the power n, or a is less than b into 2 raised to the power n. So, this is satisfied if we choose a as a n bit number. Although we can in the illustration which I took, I had taken 8 bits for the dividend, and that was with the intuition that when you multiply 2 4-bit numbers, you will get 8-bit product. So, I started with an 8-bit dividend and tried dividing it with 4-bit divisor, but there are cases where this may not work. Okay. So, we are, to begin with, we are talking of a specific case where a is a 4-bit number or n-bit number in general. That means, the left n bits will be zeros. Let me go back to this. So, although I had the right value, I was working with 8 bits, but I had the right values because I had left 4 bits 0. Okay, so this is what could happen is that if you have a larger, then algorithm may not work. So, we are trying to what we are learning here is that we will ensure that this algorithm works correctly if A is contained within n bits. Okay, now let us try to show this in general in inductive manner. Okay, so what we will do is we will use mathematical induction, assume that before a particular iteration this holds, and we will show that it holds after the iteration, that means it will hold throughout. So, there will be two cases, because in the algorithm we have a condition which is being checked and action depends upon that. So, we will take the first case. Here we assume that the invariants hold before the iteration I, okay, and we also assume this condition d into 2 raised to power n minus 1 minus 1 is less than or equal to r, which means subtraction will be carried out. So, this is one case. So, what happens in this case is what is going to be examined now. So, given to us is that this condition holds, this inequality holds, and we know that under this condition subtraction will be carried out. So, the new value of q into d plus r is given by this, where we have value of q updated. Okay, we are setting this particular bit in q, and r has changed because we have carried out subtraction, right. So, q has become q plus 2 raised to power n minus I minus 1, and r has become r minus d into this power of 2, right. So, the new value of this expression q d plus r is given by this. So, if you expand this, you will be again left with q into d plus r. So, what it means is that at least this equality holds even after the iteration. We can also check if this inequality also holds. So, the condition of subtraction is ensuring that d is less than this, okay, and we know that d into this is greater than r. So, which means that d into 2 raised to power n minus 1 n minus I minus 1 is less than or equal to r, less than or equal to d into 2 raised to power n minus I. Okay. So, so the left part of the inequality is ensured by our assumption, and the other part is ensured by noticing that invariant holds before the iteration. Okay. So, now r lies in this range, and after the iteration, once you have subtracted this quantity from r, you can see that r is going to lie in this range. Okay. So, r was in this range, from both sides you can subtract this quantity, and you can see that now after iteration r lies in this range. So, now after the iteration I also changes to I plus 1. So, therefore, we can say that for the new value of I, r lies in this range, and hence the invariant, both components of the invariant hold after the iteration. All right, is that clear? So, this was actually more difficult case which we have ensured. The other case is when subtraction is not carried out, is in fact easier. So, we assume that invariant holds before iteration and the subtraction condition is false. That means, d into 2 raised to power n minus I minus 1 is greater than r. Now, in this case the new value of q into d plus r is trivially same as q d plus r, because you are setting a bit 0, you are recording a 0, q was initially 0, So, essentially there is no change, there is no change in R. So, there is no change in q d plus R, and condition of omitting subtraction, that is this one, ensures that initially we have R lying in this range. Okay. So, basically R in the half range of this, and we are not changing the value of R. What we are changing is the value of I. So, with the new value of I, you can say that R lies in range 0 to 2 raised by n minus I. Okay. So, in this case also invariant holds, and therefore, we have rigorously ensured that we have a correct algorithm. Now, we will modify it and improve it, so that we get a suitable hardware implementation. Is there any question so far? Okay. So, now in the algorithm which I had written, we were talking of d multiplied by 2 raised power some factor. Okay. So, rather than every time multiplying by that factor, we will shift it step by step, as we did in case of multiplication. Of course, the directions of shifts may be different here. So, we start with a value in d, which is b into 2 raised by n minus 1. So, initial shift is there by position n minus 1, and then we will always ensure that d has the right value. So, that you can always subtract d from R straight away. Okay. And this will be ensured by making d shift right every time. So, we do d equal to d by 2, and this comparison becomes comparison of d and R, and subtraction becomes subtraction of d from R. All right. Also, instead of setting different bits of q, we will be shifting q left, okay, effectively multiplying it by 2 and adding a 1 or adding a 0. Okay, shift left and set the last bit, set the least significant bit by bit to 0 or 1. Okay. So, operationally this becomes easier. It is basically same thing. First time we were placing b such that there was a shift of n minus 1 position. So, we ensure that d is initialized to this number, and subsequently move d right by 1 position every time. Okay. So, once we have done this, we can draw a circuit which carries out these operations. So, you would notice that the structure is quite similar to that of a multiplier, except that the shifts are in different directions. Addition has been replaced by subtraction. So, here is a subtractor which will subtract d from R. Okay. So, R is one input, d is another input, result goes back to R. This d shifts right by 1 position every time, q shifts left by 1 position every time, and on the right side we will insert a 0 or 1 as the space gets created in q. Okay. So, there is a controller sitting here which will look at the result of comparison. Basically, we are also assuming that this subtractor is doing comparison. Okay. So, the result of subtraction is available actually at output of the subtractor. We may not store it actually if the result is negative. Okay. So, basically we are assuming that there is an indication that result is positive or negative, and this control acts accordingly. It will modify the value of R or not accordingly, and it will set a 0 or 1 in q as q shifts to the left. So, this is this circuit captures the straightforward algorithm which we had just worked out. Now, we will carry similar kind of improvements in this as we did for multiplier. Okay. We will first make sure that subtractor is reduced in size. Right now, it is a 2n bit subtraction, because d has the divider which can be placed anyway. Initially, it is quite to the left and gradually it is shifting right. So, all bits are significant at some time or the other, and therefore, we are keeping a 2n bit subtractor. What we will do is that we will change the situation and make D stationary, achieve the same effect by shifting R to the left. Okay. So, their relative position is same, right. We are shifting D right, keeping R stationary. Instead of that, we will keep D stationary and shift R to the left. So, in terms of algorithm, what we do is as follows. Now, you would notice that D will start with the value B. Okay. It is not B into 2 raised by n minus 1. D will have value B. D will be an n bit register, whereas R has the dividend placed in correct position. So, that the dividend divisor are relatively positioned correctly. Okay. So, you recall that the first time we shifted D was by n minus 1 bits and not n bits. Okay. So, the same position is maintained here, because D will be now subtracted from R in its left n positions, okay, as you will see now. We are comparing D with the higher n bits of R. Okay. R is still a 2n bit register, and I am assuming that the two parts, left n bits and right n bits, will be referred to as RH and RL, high and low. Okay. So, now it is RH or the left half of R which will participate in this subtraction. So, let me again show you this diagram. I think it will be easier if I get back to to get this same effect, what we are going to place A okay. If you shift A to left 1 bit, okay, we have, you remember that we have placed 2A in R, okay, which means A has been shifted one position left and then placed in R. Okay. So, actually what it will contain, let me get this. So, initially I would have obtained this position, sorry, not writing very cleanly. Okay, I have placed A 1 bit shifted left, okay, and B will be compared in this position. So, it is, I am sorry, So, this is R H and this is R L, and I will always be working with D, which is n bits, and R H, which also is n bit. Okay. So, they will be compared and subtraction will be carried out. So, the next time r will be shifted left, d will remain here. Okay. Instead of shifting d, we are shifting r left. So, the starting position is here, which must be carefully noted. Okay. So, coming back to the same point, we are comparing d and r h, and if this condition holds, r h becomes r h minus d. Okay. And this part is same, q gets 2 q plus 1. If the condition does not hold, q gets, I am sorry, this should have been, ignore this, let me correct this. If the condition does not hold, q simply shifts left, okay, and r is also shifted left now, right. So, with these two changes, we can have a circuit now that subtractor is only n bits, size of register d is reduced, and both the registers shift in same direction. So, now the next modification is very straightforward. We have r shifting to the left, okay, and as the positions get vacated here, we can keep on stuffing the bits of q. So, do not need to keep a separate register for q, and utilize the part of r towards the right hand, which is getting vacated to accumulate the bits of q. So, that is a very straightforward change, and we have omitted register q here. So, we are basically doing r equal to 2 r plus 1 or r equal to 2 r. So, effect of shifting q and r is sort of combined, and at the end of the iteration, r h, the left half of r will contain the remainder and right half will contain the quotient. So, same 2 n bit register contains the results. Okay. So, this leads to a circuit which is now in the final form, where we have one register shifting, another register which is n bit, and a simple control which looks at this result of subtraction and looks at the sign and accordingly controls the operations. Okay. Now, this we will introduce another form of division, which is called restoring division, where what we do is this step which was there, where we are, I am now getting back to the first form of the algorithm, where we had just introduced, after the basic algorithm we had introduced the shifting operations. Okay. So, we were comparing d and r, and accordingly we were subtracting. So, this is called actually non-restoring approach. We first check and then subtract. An alternative is that we carry out subtraction in anticipation, and if we have made a mistake, then we restore or we make a correction. So, that is called the restoring division. So, this was complete step 2 as I listed here, and in restoring approach it changes in the following way. We subtract unconditionally, and the next step in the within the iteration is that if now the result is negative, then you correct, make r equal to r plus d. Okay. Rest of it will remain same. It is in this case q becomes 2 q, and in the other case 2 q plus 1. Okay. So, if r is not negative, then you do not need to make any correction. Okay. And d part d equal to d by 2 and I plus is common. So, basically change has occurred here, that we have introduced an unconditional subtraction and there is a conditional addition. So, now in this case we are actually using 2 steps in the iteration. Okay. So, 2 clock cycles would be used, because first you have to carry out subtraction, it is only then you can carry out addition. So, apart from the fact that you are using additional steps, the subtractor has to be replaced by a circuit which can do addition or subtraction, but that is not a big deal. We have seen how that can be done. The motivation for doing this is what is going to follow, that we can actually postpone this restoration by making this following observation, that if you are restoring now in any particular step, you are restoring by adding d to r, right, and in the next iteration there will be again initial subtraction, d would have reduced by a factor of 2. So, now you are adding d, and in the next iteration you will subtract d by 2. Okay. The same effect can be achieved by not doing any restoration now, and in the next iteration the initial unconditional subtraction may be replaced by addition. Okay. So, adding d now and subtracting d by 2 later is equivalent to subtracting adding d by 2 later. So, what we are doing is that we are avoiding an additional step of restoration now, and achieve the same effect by choosing the initial unconditional step to be either a addition or a subtraction. Okay. So, the algorithm now looks like this, that initially we look at the sign of r, okay, because possibly there might be a pending restoration requirement. In the previous iteration we might have subtracted where subtraction was not to be done, and as a result we may have a negative r value. So, if r is negative in the beginning of the iteration, we make it r plus d, okay, else we make it r minus d as usual, right. So, r negative r implies that there is a pending restoration which we have postponed, and therefore, we start with an addition. Otherwise, the normal case we start with a subtraction. So, I am still showing a separate step where after this we are recording a bit 0 or 1 in q, and d is halved, I is incremented, and this is that completes the iteration. So, now of course, I have not yet eliminated 2 steps, I still have 2 steps, but I have just taken care that restoration is postponed. Okay. So, in each iteration you are doing only one addition or a subtraction. Earlier there was a possibility of one addition and subtraction both in same iteration, and they had to be necessarily done in sequence. Now, in this with some modification we can actually coalesce these 2 steps. But one important thing is that since you are postponing your restoration in the last step, if you postpone and no more iterations are left, you may still have a pending restoration. So, a final adjustment may be required here. So, I am adding a step there. At the end, if R is negative finally, then you would need to make a final correction. Okay, we will improve it further, where we are actually combining the two steps. So, recording of that bit in Q is actually brought within this condition in a single step. So, if R is negative, then you are doing initial addition, and you are here you make Q equal to 2 Q minus 1. Otherwise, you start with initial subtraction and make Q equal to 2 Q plus 1. So basically, what you would notice is happening is that as you are doing, let us say this is an anticipatory subtraction which you do, okay, and in anticipation you are also recording a bit 1 in Q. So, later on when you possibly correct this, you also would correct this effectively, right. So, recording of bit in Q is also done in anticipation and possibly corrected in the next step if necessary. So, that effect is achieved by doing 2 Q minus 1, and this part remains as it is, and there is a final step. So, now finally, also we may require a correction in Q. So, this is a step which if R is negative finally, we have a correction done in R as well as in Q, right. Okay. So, let me you want me to illustrate how this correction Q is getting done, or you can see it through. Okay, let me illustrate this. So, what will happen is that, see, let us say we have some bits of Q, we have reached some point, and let us say we have put 1 in anticipation, okay. And if it is getting if it is correct, it will be left as it is. If in the next position we are doing correction, then we will be subtracting 1 from this position, okay, next to it. So, which means this 1, I mean, if you just see locally this 1 0, and from that you are subtracting 1, it will become 0 1, okay. Or if let us say if this need for correction continues, right. So, if you are subtracting a 1 again here, then this 1 also becomes 0, and you get a 1 here, and so on. So essentially what is happening is that the 1 which you had put in anticipation gets converted to 0, and you are putting a 1 in the next position, and if even that is not correct, next time when correction is done, even that gets moved further, okay. So, I will suggest that you actually take some examples and work through the algorithm, so that you have convinced yourself that it works correctly. Okay. Now, once we have brought the algorithm to this form, effectively we have now made it almost ready for a sign division. Okay. What is effectively happening is that in every iteration, by adding or subtracting d, we are trying to bring r closer to 0. Okay. You are starting with some value, and your attempt is to bring it successively close to 0. Okay. So, you subtract initially large value, then you subtract or add half of that, then half of that, and so on. So, essentially you are trying to bring it close to 0, and if we observe it in that sense, whether the value was initially negative or positive, it can still work. Okay. If the dividend was negative, we are still, by adding a positive value, we will bring it close to 0, or if divisor was also negative, by subtracting divisor we will bring it close to 0. So, essentially attempt is to look at signs of r and d, and accordingly either subtract or add. So, instead of checking whether r is positive or negative, we will see if sign of r and d are same or different. If they are different, then we subtract, sorry, if they are different, then we add, because if opposite sign values are being added, then the result will be smaller, and if they are of same sign, then we subtract. So, that is the change in the logic. I am looking at the MSB of R and D, the sign bit, and if they are not equal, then we add, otherwise we subtract. Okay. And accordingly q becomes 2 q minus 1 or 2 q plus 1, right. So, that is the only change, and we can use the same thing for a signed division. The final correction step also makes a similar check. It compares r n minus 1 and d n minus 1. If they are still of the opposite sign, then there is a final addition which is being done. So, now intuitively is this correct? What is the relationship between signs of dividend, divisor, quotient and remainder? So, let us have a look at that. So, we are given basically dividend and divisor, and we are looking at all possible sign combinations. Any of these could be positive, any of these could be negative, and the two right columns show the corresponding signs of quotient and remainder. So, what is the logic which is intuitively governing this? That sign of the quotient would follow similar logic as you have in multiplication. Okay. When you multiply two numbers of same sign, okay, that is positive into positive or negative into negative, result is positive. So, same thing we will do. You are dividing a positive number by a positive number, you get a positive quotient. You divide a negative number by a negative number, you get a positive quotient. Okay. Oh, where has it gone? Okay. So, the quotient is following same logic as multiplication, right. So, when the signs are opposite, the quotient is negative, when signs are same, quotient is positive. The remainder always takes the same sign as that of dividend, because remainder is something which is left out of dividend. You try to reduce the dividend to 0, but something is still left. So, it has to be of the same sign, and if you look at this, so final correction actually which is being made here will ensure that remainder is ultimately of the same sign. Just a minute, this is no, actually that's not obvious from here. I think it is one could prove that remainder would be of same sign, although it is not obvious from this condition. Oh, well, actually, I would like you to, I have written several algorithms, and the kind of proof I did using invariants, you should try for a few more, okay, particularly this one, right. So, you should ensure that the correct signs are being obtained here. In particular, the remainder should be of same sign as the dividend, and the quotient would depend upon whether the sign of divisor and dividend are same or opposite. Okay. I leave it to you to ensure that very rigorously. Okay. So, let me summarize what we have done. We started with simple hand worked example of 4-bit division in unsigned case, and we noticed that using basically compare, shift and subtraction operations, you can carry out division in a sequential manner. So, based on that we developed the basic algorithm, we analyze it thoroughly to ensure that it is correct, and from there we derived the circuit. In the circuit, then some improvements were made. First improvement was to reduce the size of the subtractor. Instead of a 2 n bit subtractor, we reduced it to n bit subtractor, and then we did some improvisation and reduced the number of registers. So, ultimately we worked with one n bit register and one 2 n bit register. Then we brought in the concept of restoring division. So, initially you carry out anticipatory subtraction. So, there is no comparison involved here now. Subtraction is done unconditionally, or I should say blindly you subtract and then restore. Then we saw that restoration can be postponed, which simplifies each iteration, and of course, it made it necessary for us to have a final step where a final restoration or final correction was necessary. Then with slight changes, we were able to modify this algorithm for signed numbers, and remember that when you are talking of signed division, we are doing addition subtraction with 2's complement number. Okay. So, therefore, the addition subtraction need not be done, or addition subtractions are not conscious of whether the numbers are signed or unsigned, as long as representation is 2's complement. So, that fits in nicely, and we can have the algorithm work on 2 signed integers and perform division. Okay, I will stop at that. Next time we will take up floating point operations, and with that this chapter will be done.